Okay, in this video we're going to talk about correlation. So in previous videos we talked about the variance of a random variable, and then we talked about when you have two random variables, the covariance of the two random variables. And using the covariance of two random variables, we can define a number called the correlation of the two random variables. And that's what we're going to talk about in this video. What's the correlation and what are some properties of the correlation? And what does it tell you? And this might go into two videos because there's a lot. So correlation. So suppose that, let me just, okay. So suppose that you have two random variables, x and y. And let's say that they have standard deviations sigma of x and sigma of y, which are both positive. Remember, the standard deviation, that's what I mean by SD. Standard deviation is the square root of the variance. And if the standard deviation is 0, that would mean that the variance is 0. And that would mean that you have a probability distribution which is a constant almost everywhere. Okay. The probability that x is not that constant, the mean is 0. So it's the mean with probability 1. Okay. And when you have this situation, we define the correlation between x and y, and sometimes it's called rho, but I'm just going to write COR because there's a little too many symbols. So correlation of x and y is defined to be the covariance of x and y divided by the standard deviation of x times the standard deviation of y. Well, we can write that using the definition of the covariance as the expectation of x minus mu x, the mean of x, over sigma of x, times y minus mu y over sigma y. Because we're just using the definition of the covariance of x and y. So maybe just writing out a bit more detail, recall that this is equal to the expectation of x minus mu x times y minus mu y. And then you can move this constant square root of x, square root of y inside the expectation by the linearity, and so you get this. And what's useful about writing it like this is that it might help you remember how the correlation is defined. So this x minus mu x over sigma x, if you call this u, and you call y minus mu y over sigma y v, well, what are these random variables have? What do they have in common? They both have mean 0 and variance 1, right? So what you're doing to find the correlation, one way I think about this is that you have these two random variables, x and y, and then you normalize them so that they have mean 0 and variance 1 by this kind of shifting and dividing, and then you take the expectation of the product. Now let's look at some properties of, that's the definition of the correlation of x and y. Now let's look at some properties of this. So suppose that you have two random variables, x1 and x1 and x2, and you define y1 to be a times x1 plus b1, a1 x1 plus b1, and y2 equals a2 x2 plus b2. And the question is, how is the correlation of y1 and y2 related to the correlation of x1 and x2. So when you make these shifts to x1 and x2, how these transformations, how does that affect the correlation? And the answer is that this is a1 divided by the absolute value of a1 times a2 divided by the absolute value of a2 times the correlation of x1 and x2. Now before proving this, let's look at what these factors are. These factors here. These are going to be, what values are these going to have? They're going to have values 1 or negative 1, depending on whether A1 or A2 is positive. And we're assuming that A1 and A2, of course, are not 0. So it's plus or minus the correlation of x1 and x2. That's the correlation of y1 and y2. It's either the correlation of x1 and x2, or it's negative the correlation of x1 and x2. Okay, let's prove this. Of course, we're going to use the definition and probability properties of the expected value. So we know that the expected value of yi is equal to a times the expected value of xi plus b, or this is ai and bi by the linearity. So, I mean, what we need to find is what we need to find is this. We need to find we need to find what that is. So what we will do is we will look at what is yi minus the expectation of yi. Well, that is a times ai xi plus bi minus ai minus parentheses ai expectation of xi plus bi. And the bi's will cancel, and so this is ai times xi minus ai times the expectation of xi, which we can write by factoring out the ai times parentheses xi minus expectation of xi. So what can we say about the expectation of yi minus y1 minus the expectation of y1 times y2 minus the expectation of y2? Well, this is equal to the expectation, by what we have above, of a1 x1 minus the expectation of x1 times a2 times x2 minus the expectation of x2. I don't know why my pen is doing this. It's annoying. So this is equal to a1 a2 times the expectation of x1 minus expectation of x1 times x2 minus the expectation of x2. And of course, that thing is precisely the covariance of x1 and x2. Now recall that we want to compare the standard deviation of yi to the standard deviation of xi. And we know that the variance of yi is equal to ai squared times the variance of xi. That's a property of the variance. And so when we take the square root of both sides, we get that the standard deviation of yi is equal to the absolute value of ai times the standard deviation of xi. And so therefore, the standard deviation of y1 times the standard deviation of y2 is equal to the absolute value of a1 times the absolute value of a2 times the standard deviation of x1 times the standard deviation of x2. Okay, now let's divide. So we have this is equal to this, and we have this is equal to that. And now let's divide the blue expression by the yellow expression. Then on the left, we will get the correlation between y1 and y2. And we'll see that it is precisely a1 over absolute value of a1 times a2 over absolute value of a2 times the correlation of x1 and x2, and that completes the proof. A correlation. Maybe I should write 2 R's, just so that's clear. We're not talking about the covariance. Okay. So when a1 and a2 are positive, then what happens to the correlation? So if you have x1 and x2, right, and then you take, y1 to be 1,000 x1 plus 7, and then y2 to be 1,000,000 x2 plus 9. How does the correlation of y1 and y2 relate to the correlation of x1 and x2? They're the same, right? Because your a1 and a2 are, I forgot what the numbers are, they're some positive numbers. And then when you divide by the absolute value, well, the absolute value of a positive number is the same as the number, so you're just multiplying by 1, so the correlation doesn't change. So one way to think about this in practice is suppose that x1 and x2 have units like inches, and then you convert from inches to centimeters, and so you get y1 and y2 to be random variables, but with units that are centimeters. Well, the correlation of y1 and y2 will be equal to the correlation of x1 and x2. So it's, in that sense, independent of the units that are used. So one way I think about this is if you take the height and weight, it doesn't matter if you use pounds or kilograms. So suppose that you have x and y are height and weight. Well, if you scale x and y to get different units of height and weight, then the correlation of those two new random variables will still be the same as the correlation of the random variables that you had when you measured with different units. Okay. So let's look at a consequence of the theorem we proved. So what's the connection between the correlation of x and y and the correlation between x and negative y? Well, here we're taking negative y to be negative 1 times y, right? And we're taking, so it would be like if you had a1 equals 1 and a2 equals negative 1. So we see that the correlation of x and y is just negative the correlation of x and negative y. Or, well, it doesn't matter where you put the negative sign. Negative correlation of x and y is equal to the correlation of x and negative y, which means that the correlation of x and y is negative correlation of x and negative y. That's an example. Okay. There's something called so there's an important fact about the correlation, which is that the correlation is always between -1 and 1. Whenever you have two random variables, the correlation is between -1 and 1. And we'll prove this later, because it's a somewhat complicated and involved proof. But what I want to talk about in the rest of the video is how to use the concept of correlation to come up with a linear prediction relating x1 and x2. So suppose that you have x1 and x2, which are, of course, random variables. So what we want to do is, suppose you suspect that x2 is related to x1 in a linear way. And what you want to do is you want to find the best linear function of x1 to approximate x2. So one way to phrase this is we want to pick a and b to minimize, so a and b are numbers, that will minimize the expectation of x2 minus ax1 plus b squared. Okay. So this is called the mean squared error. So what a and b will minimize this quantity? That's the question we ask. Let's see what this thing is. You distribute all of this out. So this thing is equal to the expectation of, okay, we have to write all this out. It's going to be x2 squared minus 2x2 times ax1 plus b plus ax1 plus b squared. This is not complicated. I think I'm not going to go over this in detail. I mean, you just expand the inside, expand this thing out, and you see that you get this. Now we apply the linearity, and then we get that this is the expectation of x2 squared minus 2 times. Okay, now we have to distribute this across. So it's 2a times the expectation of x1, x2 minus 2b times the expectation of x2 plus a squared times the expectation of x1 squared plus 2ab times the expectation of x1 plus b squared. So let's make sure we understand what's going on here. What are the numbers and what are the variables? Well, we're trying to pick a and b that make this as small as possible. So we're thinking of this as a function of a and b. So a and b are the things that are varying. And the other things are constants, right? The expectation of any random variable is going to be a constant. So you have this e of x2 squared, that's a constant, e of x1, x2 is a constant, e x2 is a constant. Everything that's e with something in brackets is a constant. And now you have a function of two variables, a and b, right? So going back to your multivariable calculus, if you have a function of two variables, x and y, how do you find the x and y that will make this as small as possible? You want to find the critical points of this function. And you have to think about how many maxima and minima you have. I mean, if you have several local maxes and mins, then your value might not be an absolute max or absolute min. But if you only have one, just think about like a bowl. And if you only have one local minimum, then it's going to be an absolute minimum. And if you have one local maximum, it's going to be an absolute maximum. So let's see what we get. So we take the partial derivatives of both sides. Not both sides. We take both partial derivatives, right? We take partial derivatives with respect to A and B. And so let's just call this like f of A comma B. And A and B are variables here. So when you take partial f partial A, this is going to be -2 times the expectation of x1, x2 plus 2a times the expectation of x1 squared plus 2b times the expectation of x1. And if you take the partial derivative of f with respect to b, then you're going to get -2 times the expectation of x2 plus 2a times the expectation of x1 plus 2b. And we set these equal to 0, and we're solving for a and b. Suppose we multiply the second equation, so let's call this star and double star. If we multiply the second equation by negative expectation of x1 and add to the first equation, what do we get? Well, the middle terms are going to cancel. So you are going to get -2 expectation of x1, x2 plus 2 times the expectation of x1 times the expectation of x2. Oh, and then the other terms are going to cancel too. So it's not just the middle terms, it's also the last terms are going to cancel. So this is going to be 0. And now you divide both sides by 2. And so you're going to get am I doing this wrong? Oh, sorry, the middle terms did not cancel. Only the last terms cancel. I just read the thing wrong. So it's going to be this let's see, plus 2a expectation of x1 squared minus 2a times the expectation of x1, and then this whole thing squared, right? That's squared. That is going to equal 0. And now we divide everything by 2, and then we solve for a. So we're going to get -2 expectation, we divide by 2, right? So negative expectation of x1, x2 plus expectation of x1 times expectation of x2 plus a times expectation of x1 squared minus a times the expectation of x1, and then this whole thing squared equals 0. And now we get these terms on the other side. So we are going to get, these go to the other side, and so we're going to get a times the expectation of x1 squared minus a times the expectation of x1 squared equals expectation of x1 times expectation of x2 minus the expectation of x1, x2. And now you factor out the a and divide, and so we get that a is going to be the expectation of x1, x2 minus the expectation of x1 times the expectation of x2 over the expectation of x1 squared minus the expectation of x1 quantity squared. And this is the, on the numerator, I have the covariance of x1 and x2. And then what do I have on the denominator? I have the variance of x1. So A is equal to the covariance of x1 and x2 over the variance of x1. Now I can write this in terms of the correlation, because the covariance of x1 and x2, remember we defined the correlation to be the covariance of x1 and x2 divided by the standard deviation of x1 times the standard deviation of x2. So let's use sigma 1 and sigma 2 for the standard deviations of x1 and x2. Then the numerator is going to be the correlation of x1 and x2 times sigma 1 times sigma 2, and then on the denominator I have sigma 1 squared. So the sigma 1's cancel, and so I get the correlation of x1 and x2 times sigma 2 over sigma 1. So that's what A is. Now let's solve for B. Well, for B, we can use the second equation here. So if you plug in A, let's divide both sides by 2. We get that B is equal to expectation of x2 minus A times expectation of x1. So that's mu2 minus A mu1. So let's write that down. B is equal to mu2 minus A times mu1. So what's the so-called the best straight line fit? Well, it's A x1 plus B. Now here x1 is a random variable, so this is really a function, right? It's the linear function that most closely approximates x2. So this is going to be the correlation between x1 and x2 times sigma 2 over sigma 1 times x1 plus mu2 minus A mu1. And I can write this as mu2 plus correlation of x1 and x2 times sigma 2 over sigma 1 times x1 minus mu1. Now, if we think of x1 and x2 as like variables, like x and y, then notice that when x1 is mu1, okay, you get mu2. So this linear function sort of goes through the point. If this were a line, it would go through the point mu1, mu2. So it goes through the means, and the slope is correlation of x1 and x2 times sigma 2 over sigma 1. That's the best linear predictor of the random variable x2. Okay, we'll do more examples of this in the next video. And then we also have to talk about the Cauchy-Schwarz inequality and then how we get that the correlation is between -1 and 1. Okay, thanks.